Hi everyone. Today we're going to be having a look at the first part of our next topic, which is on radioactivity. So today we'll be having a look at different types of radiation, having a closer look at the actual nuclei and what happens inside the nuclei, and what is alpha decay. So the SACE outcomes related to our work today is we're looking at what is the difference between a stable and unstable nuclei, and looking at the proton to neutron ratios inside of the nuclei there, and having a look at something called an N versus Z graph, and how that relates to the stability of different size nuclei, and what type of radioactive decay that means is more likely to occur. So we'll learn how to read those graphs and state the characteristics of which region corresponds to which type of decay. And then we'll be going into a little bit of detail about alpha decay, so looking at the charge and mass and nature of alpha and gamma emissions, and balance some equations and talk about why the emitted particles have the energy that they do. Alright, so there are three different types of radiation, and they were discovered by a guy named Ernest Rutherford. And so he set up an experiment. You can sort of see the outline down the bottom, and he discovered that different types of radioactive particles behave really differently when you apply them in a magnetic field. So using that information, he was able to discern that they had different charges, and the amount of deflection that he observed actually related to the size of the particles. So he called these different particles alpha, beta and gamma radiation. So the first of our SACE outcomes was to using the properties of the attractive nuclear force and the repulsive electrostatic force between protons. We have to be able to discuss the reason for the increase in the neutron to proton ratio for stable nuclei as we see larger nucleus and the atomic number increases. So let's have a look at more detail in that. Alright, so nuclear stability. So here we have a really simplified diagram of the inside of a nucleus. And we know that in between like charges, the Coulombic repulsion acts between the protons. So because the only things that are charged in the nucleus are the protons, then we have this repulsion acting between the protons. So we also have what we discussed the other week, which was about nuclear force. So the nuclear force acts to hold protons together, but it's too weak to overcome the Coulombic repulsion between the two positive charges. The good thing about the nuclear force, though, is it doesn't discriminate who it actually attracts. So the nuclear force also acts between the protons and the neutrons, and between the protons and the protons. So you can see all of the green arrows that have been added there. So this is actually what makes our nucleus stable. So a nucleus with too few neutrons is going to be unstable, because that nuclear force won't be strong enough to overcome the Coulombic repulsion between the positive protons. And similarly, a nucleus with too many neutrons is also unstable, because we don't have a nice balance of the forces. So for really small nuclei, approximately equal numbers of protons and neutrons, they tend to be more stable. In a large nucleus, a proton on one side will only be attracted by the nucleons that are closest to it, and it'll be repelled by all of the other protons. So because of that, the nuclear force only acting over really tiny distances, the rest of the neutrons don't have any effect, and they don't try to dampen the repelling force between the protons. So you tend to be more unstable. So the larger nucleus, the more neutrons need to actually be added to provide the nuclear force close to all the other protons in order to hold it together. So there is, even that being said, there's still a limit onto how big a nucleus can actually get and continue to be stable. So stable and unstable nuclei continued. Nuclei like this are, we have deuterium, which is 1 proton and 2 neutrons, and we have helium, which is 2 protons and 2 neutrons, and then we have carbon, which is 6 protons and 6 neutrons, and oxygen, which is 8 protons and 8 neutrons. So this 2-to-1 proton nucleon ratio holds up until around a atomic number of 20. So after that, it tends to blow out a little bit in terms of the number of additional neutrons that are required to balance out those repelling forces. So a stable nucleus, it doesn't disintegrate in any way unless it's given additional energy and wants to return to its ground state, and that way it may disintegrate. However, an unstable nucleus, if it doesn't like to be stable, it will disintegrate of its own accord, and this is called undergoing decay. And basically it will do this in a few ways. It might emit alpha particles, which are essentially helium nuclei, or it might emit something called a beta minus, or a little Greek B minus particle, which is a negative electron, or it might emit something called a beta plus particle, which is something called a positron. So as I just said before, there's a couple of different ways that an unstable nuclei might decay and try to become more stable. So the first way is to undergo alpha decay, in which case a helium nucleus, so that has 2 protons and 2 neutrons without any electrons, is emitted from the unstable nuclei. And so this occurs when we have an atomic number above 83. The other type of decay that could happen is called beta minus decay, and in which case an electron is emitted. And so this occurs normally along the NZ line, which we'll have a look in a minute. So that occurs above the line of stability. And then we have something called beta plus decay, in which case the positron is emitted, and this occurs when the plot lies sort of below that line of stability. The other type of thing that can happen is something called spontaneous fission, where the nucleus just splits into 2 different parts. So the next few outcomes related to that N versus Z graph that I just mentioned. We have to be able to use that graph to indicate the corresponding regions relating to alpha decay, beta minus decay, and beta plus decay. So if we have a look at that now, we also have to use it to predict the likely types of decay that a nucleus is more tending to undergo, and what characteristics of each region correspond to each type of decay. Alright, so over here we have what is called an N versus Z graph, and so N standing for the number of neutrons and Z being for the number of protons, or the atomic number of the particular atom that we're talking about. So as you can see there, as we go further to the right, our number of protons is getting really big. So in the middle here, we've got something called N equals Z, so equal numbers of protons versus neutrons. And you can see along that red line, up until about 20, most of the elements kind of fit somewhere along there. And that's what we said before, how it's going to be, for about 20, you have the same ratio of protons to neutrons. After that, the stability line, if we follow it up through the middle there, that white line, tends to have more neutrons than protons, but in that white region is still, it's still a stable nucleus. So larger nuclei, so the ones that have a really big Z number, a big number of protons, they tend to undergo alpha decay and spontaneous fission, so that last type that we talked about. So these are going to be the ones located in this sort of orange region up here. So because they're so big, it's very hard for them to be stable, and to become more stable, they break apart into some smaller, more stable subsets. Then we have the green section. So the green section are the ones located above our proton and neutron sort of line. So these ones are going to be nuclei with too many neutrons, like they've got additional neutrons. And so they tend to undergo beta minus decay. If they have too few protons, too many neutrons, they want to convert one of their neutrons into a proton so that they can then be more stable. So that's called beta minus. Over here, we have nuclei that are opposite to that. We have ones that have too many protons and not enough neutrons, so the opposite needs to happen. Some of those protons need to be converted into neutrons, and that, because they're getting rid of a plus, is called a beta plus decay. Alright, the last outcome related to alpha decay. So we need to look at the charge, mass and nature of alpha. In particular, we're just looking at alpha emissions and balance nuclear equations for this type of decay, and explain about the energies, why they have discrete energies, these alpha particles, when they're emitted. Alright, so alpha decay occurs in really large nuclei, so ones that have an atomic number greater than 83. And the main reason that it occurs is because the nucleus has too many protons, and because the protons repelling each other, there's not enough neutrons and there's not enough nuclear force to distribute in amongst those protons to try and dampen that down. So the coulombic repulsion between the positive protons it causes excessive repulsion, and as a result we have in the middle here, if you have a look at the diagram, we've got the parent nucleus or the original nucleus. We have the smaller nucleus that happens when the repulsion happens, and as that repulsion happens, a little alpha particle is ejected out. Now that ejected out alpha particle, as I said before, is nothing more than just a helium nucleus. So in an alpha decay, the mass number decreases by 4 and the atomic number decreases by 2, and that makes sense if we think about it in terms of a helium nucleus. So in a helium nucleus, helium has 2 protons and it has two neutrons. So it has a total mass number of 4 and an atomic number of 2. So of course, if that particle is being ejected out of the nucleus of the big atom, then that big atom is going to reduce by 2 and 4 respectively. So here we have what it would be written as a chemical formula. So over on this side of the equation, we've got our what's called the parent nucleus, and it has its mass number and its atomic number, and we can see that after the reaction has happened, or after the decay has happened, our atomic number is reduced by 2 because it's lost 2 protons, and its mass number is reduced by 4 because it's lost a total of 4 nucleons, and they have been found by this alpha particle or this helium nucleus. So if you added up all of the total number of nucleons on each side of the equation, it would still be equal. So a real example, rather than having pluses and minuses, is uranium-238, and that is undergoing decay to thorium-234, and you can see there that the thorium has 4 less of its mass number and 2 less of its atomic number, because it is ejected out this alpha particle or this helium nucleus, where you can find that the missing numbers. Alright, so when these alpha particles are ejected from the parent nucleus, they're emitted with really distinct energies. So this is because there's only a certain amount of energy involved in the decay. So the energy is divided up between the nucleus and the alpha particle, and it's in inverse proportion to their masses. So depending on the original mass of the parent nucleus will depend how that mass is divided up.